Okay, folks, continuing along, let's get into this next learning goal, 1.2. Know the four molecular modes of motion and how they connect to statistical mechanics. Okay, so we are just taking a little bit of a crash course or an introduction into statistical mechanics. In some curriculums or even in graduate school, this would be an entire course. But I like to weave this topic into thermo because as we can see here in StatMech, is what we call this colloquially, we connect macroscopic properties in thermodynamics like temperature, pressure, and so on. And we're going to connect those macroscopic properties with microscopic properties governed by these molecular modes of motion. Okay. So I like to think of these molecular modes of motion as the four things molecules can do. So let's start at the beginning. So in the electronic mode of motion, this is how electrons within molecules can absorb energy and transition from one electronic state to another electronic state. So we typically see this in spectroscopy, right? At least in visible spectroscopy, as we'll see. And if we look at a typical spacing, let's say between the ground state to the next highest state. And so obviously we can see in the electronic levels, they crunch together as we go up and up and up. However, if we just focus on a typical spacing between the ground state and the next excited state, that could be anywhere between 1 and 10 electron volt for like a single atom or molecule, or for a large collection, that's about 1,000 kilojoules per mole. Okay. So if we had about a mole of molecules going from state 1 to state 2, it would take about 1,000 kilojoules, or 1 megajoule. So now if we see how the vibrational levels map out onto the electronic levels, if I zoom in here, I'm going to draw a box around this ground electronic state. Well, as it were, all of these vibrational levels that we see could fit entirely within this vicinity near the ground electronic state. And thus, of course, we could have our vibrational levels going up just the same way as the electronic levels, 1, 2, 3, 4, etc. As we will go down the rabbit hole and learn more about this, we'll see the vibrational levels are evenly spaced, so they don't go up in this fashion like the electronic levels. And again, if we were to look at a typical transition from the vibrational ground state to the next vibrational state, we would see that that's about 0.1 to 1 electron volt, or anywhere between 10 and 100 kilojoules per mole. So quite a bit of difference in energy from the electronic levels to the vibrational levels. And similarly, if we were to zoom in on any one vibrational state, let's pick the ground state, we could see a whole bevy of rotational states would fit within that one level. And you can see the rotational levels go up. They spread out as they go up. We'll explore that in more detail as we go. And if we were to look at a typical energy spacing in the rotational levels, those are going to be on the order of milli electron volts. So 1/1000th of an electron volt, or on the order of about 10 joules per mole. And of course, similarly, if we were to zoom in on any one of these rotational levels, we would actually see this continuum. So I'm going to write that down. Continuum of translational levels. And so these translational levels are how the molecules actually move around in XYZ dimension. And these levels are so finely spaced together, right? I'm kind of like shading all of this in, that they don't appear to have levels at all. In other words, it's this continuous amount of energy that can be pumped into the translational levels, as opposed to specific, like exact quantized levels that need to be pumped in to the rotational, vibrational, or electronic. So those are molecular modes of motion. And their populations, or in other words, what percentage of molecules exist in a given state of a given collection, will govern temperature and pressure and the like. So we want to think of the three main postulates of STETMEC. Okay, that says postulates, three main postulates. The higher the energy of a state, the lower its population is at a certain level. So in other words, if an energy state is way up the ladder, right, some really high energy state, it will be very likely, statistically speaking, that higher energy state will have a very low population. So not very many molecules will exist in that higher energy state. Okay. Conversely, the higher the temperature of a state, the higher its population. So you can see I made a typo there, so I had to fix that. So what that means now is if we take some collection of molecules and we increase their temperature, they will auto-populate the higher levels. So we will have provided them with enough thermal energy to promote them into higher and higher energy states. And number three, more states are populated if they are closer together. So just like we saw with the vibrational and rotational levels, their levels get closer and closer together. We see that there is a lot more of those molecules spread out in those various states. So if we think about the electronic state, it is such a big gap here from level 1 to level 2, 1 to 10 electron volts, that nearly everything exists in the ground state at room temperature. In the vibrational levels, almost everything exists in the ground state. However, in the rotational levels, those energy levels are fine enough together. They're close enough together that there is a multitude of states occupied. Okay. So now if we kind of think about these energy levels, and these are generic, okay, so these don't necessarily correspond to any of those molecular modes. By definition, at 0 Kelvin, everything, 100% of our molecules, atoms, ions, whatever we're talking about, will be in the ground state. By definition, that is what 0 Kelvin means. If we look at 298 Kelvin, we will see a population of states. Okay, so that says population of states. So in other words, we might see some percentage in the ground state, followed by perhaps an increasing percentage in the next state, followed by maybe slightly more in the state above, followed by slightly less and even less. In other words, if I were to tip this on its side, it would look like some kind of a bell curve, right? We would see some type of statistical distribution of these states, where one of these states would correspond to the most populated. And if we could achieve such a thing as infinite Kelvin, if such a thing were possible, then technically all of our states would be simultaneously populated at the same level. So again, that's why this would be not totally feasible. However, on our way to approaching infinite Kelvin, or more realistically, on our way to approaching some very, very high temperature, all of our states start becoming enormously populated, okay? And of course, if we weren't at infinite Kelvin, but maybe something like 10,000 or even 10 million Kelvin, we would see a population. We wouldn't get like 100% in each state. We would see a distribution. Okay, I'll see you in the next video. That's good enough for now in our crash course introduction to statistical mechanics.